In this lesson, we're going to examine another type of discrete probability distribution, one called binomial. A binomial distribution occurs when you have repetitive independent trials. So you can do something more than once. Maybe you flip a coin. And you flip it a couple times and you're repeating itself, and they're independent because one flip has no effect on the next. And what we're going to do with this is we're going to try and count the number of successes. Okay, so how many times did I get something? So again, if we go back to the coin idea, we're flipping a coin 10 times. I want to count how many tails I got, maybe. Okay. To do this, we have a formula for the probability now. Probability is, and it's kind of complicated here, is made up of a couple things. Okay, we're made up of a combination, because the order that we get successes in doesn't matter. What matters is how many successes we have. So n choose x stands for n is our number of trials, how many times we're going to do something, and x would be your number of successes. How many times you were successful, how many times you counted the number of heads, let's say. And then you have p. P is the probability of success on any individual trial to the power of x. Again, x is our number of successes. And q, which is calculated by 1 minus p, the complement to success would be failure. And the exponent there is n minus x. And it seems very complicated. We're going to try a couple, and you'll see actually it comes up pretty easily. So first example here. Create a probability distribution for the number of heads when a coin is tossed 6 times. So in this case, n, number of trials, would be 6. X is going to change. X is the number of heads we get. We'll look at that in a second. P is our probability of success. What's the probability of getting heads on a single toss? Well, it's 1/2. And Q would be the opposite, the complement, 1 minus 1/2, which in this case is also 1/2. So our distribution, how is this going to work? X is the number of heads we could get. So I could have none, or 1, or 2, or 3, or 4, or 5, or 6. P is my probability. So the first one, I have a coin, I'm going to toss it 6 times, and I want to have no successes. The likelihood of success is 1/2, but I want that to happen no times. Failure is also 1/2, and I want that to happen 6 times. So if we use our calculator for that one, we end up with 0.015625. Keep all the decimals. Next option, I could have 1 success. So somewhere in those 6 I want to happen once. Okay, it's a combination, order doesn't matter. Okay, my chance of successes happening is 1/2. I want it to happen once. I want to fail 5 times. And that gives us 0.09375. Okay, next one, 6 choose 2. I want 2 successes. The likelihood of success is 1/2 twice. I want to fail 4 times. And we get 0.234375. And then the next one, 3 successes. Success happens 3 times. Failure happens 3 times. And we get 0.3125. All right, 4 successes. I want 4 successes. I want 2 failures. It turns out for this one, it's 2344375, which we've seen already. And the next one, 6 choose 5. 5 successes, 1 failure. And that number comes out to, no surprise to anybody here, 0.09375. And the last one, 6 choose 6. I want to be successful every time. So I want 6 successes. I want no failures. And I get 0.015625. Now, the nice thing in this one is there's symmetry. The reason there's symmetry is because P and Q were the same. If P and Q weren't the same, you won't have symmetry. So unfortunately, it's not the shortcut. You can just fill in the first half of the table and you know the second half. It's a special circumstance where P was the same as Q. But the idea of the formula, I think, is actually not that bad once you get the hang of it. Okay, we're going to try another example. A pair of dice are tossed 5 times. Find the probability that doubles comes up exactly 3 times. So n is 5. We're doing 5 trials. P, my probability of success is getting doubles. That's what I'm trying to get. How many ways can I get doubles? There are 6 of them. 1s, 2s, 3s, 4s, 5s, and 6s out of the 36 ways you can toss a pair of dice. Let's simplify that. So P is 1/6. Q is a complement. So 1 minus a 6 is 5/6. Now, I could make the entire distribution. There's nothing wrong with this. How many times do I get doubles? None, or 1, or 2, or 3, or 4, or 5, or 6. But the question this time doesn't want all of them. It wants to know exactly 3 times. It wants to know just this one specific case. So the idea of the binomial distribution is, yes, I can make the table, but I don't want to have to make the table. I want to look at just that one case. So we're going to figure out the probability that x is 3. There's specifically 3 cases. How do I do that? Well, there's 5 trials. I want to be successful 3 times. My likelihood of success is 1/6, 3 times, and failure 2 times. Into my calculator that goes, and we get 0.0321. Okay, so I don't want you to make the entire table the whole time unless it says, hey, make me a probability distribution. We want to look at specific cases. Let's try part B. A sum of 12 comes up at least once. Okay, so what n is our trial? Still 5. P is getting a sum of 12. The only way that can happen is if we get a 6 and a 6. There's one of the 36 ways of doing that, which makes Q 35 out of 36. Now the question this time didn't say get exactly one sum of 12. It says get at least one sum of 12. In other words, if I'm thinking about this table, x and px, I could get a sum of 12, none, 1, 2, 3, 4, 5. I want to know at least once. In other words, I want to know all of these cases. When we're thinking about all of these cases, at least once, I'm thinking greater than or equal to 1. In other words, what's the probability of 1 plus the probability of 2 plus the probability of 3, 4, and 5? But we know there's a faster way of approaching these kind of situations. Let's get rid of what we don't want, this one, and be left with what we do want. We can get rid of what we don't want by taking the idea of I know what a distribution adds up to. The whole table has to add up to 1. So if I take 1 and I subtract the case that I don't want, which is 0, I can figure out the probability of at least once getting a sum of 12. So ready for our formula. There are 5 successes. I want to have no successes. Likelihood of success is 1 out of 36. I want that to happen no times. And I want to fail 5 times. Okay, I can put this all in my calculator at one time, and if I do, I get 0.1314. There's the likelihood of at least one sum of 12. It saved me from having to add up this number, and this number, and this number, and this number, and this one. Right? Way faster. Okay, you guys are going to try one. So pause it, see what you can do with this. The factory makes switches. The probability of the switch is defective is 0.04. They test a random sample of 100 switches. What's the likelihood of exactly 6 defective ones? So I'm not looking for the whole thing, I'm looking for just specifically 6. My trials is the number of things I've tested. There was 100 of them. I want to find 6 defective ones. The likelihood of defectiveness is 0.04. I want that to happen 6 times. Likelihood is not defective would be the opposite, the complement, so 0.96. And I want that to happen 94 times. If you do it, you should get 0.1052. Okay, part B, at least one defective switch. So I could go through all the cases, 1 defective switch, 2 defective switches, 3, 4, 5, 6, 7, all the way up to 100 defective switches. Or smarter, get rid of what I don't want. I don't want 0. Okay, 100 cases, I don't want any defective switches. The likelihood of a defective switch is 0.04, and I want that to happen no times. I want to be not defective 100 times. What's the likelihood of that? Well, I get 0.9831. Okay, part C. How many defective switches should you expect to find in the sample? Well, if you stop and think about it, 0.04 is the same as saying 4%, right? So really what I'm asking is, well, how many expected switches should I get if, on average, there's 4% effectiveness? If there's 100 switches, doesn't it make sense, logically, 4% of 100 is just 4. I would expect 4 defective switches. I don't need any complicated math for this. I can use some common sense in saying if I know a percentage and I know how many things there are, I can figure out what I should expect. Okay. Mathematically, the rule here is the expectation for a binomial distribution is find your average. Okay. If there's n trials, how many times you do experiment, and success is p, then the expectation is just n times p. In our previous one, 100 times 4%. 4. It's a common sense. Okay, last question. Paula goes to work 3 days a week. On any day, the probability she gets on a red bus is 1/4. What's the expected number of times she goes to work on a red bus? Okay, well, how many trials? She goes to work 3 days a week. On any one of those days, the red bus is 1/4, so she should expect to get on a bus that's red 0.75 times. Again, it's theoretical. She can't get on a bus 3/4 of the time, so the odds are it's probably 0 or 1. That's what's going to happen. Right? Just like any other distribution, expected values are just theoretical. And let's try part B. In 1 week, find the probability she goes to work on a red bus exactly 2 days. So I want a probability of being 2. How many trials do we do? She rides the bus 3 times. I want 2 of them to be red days. The likelihood of getting on a red bus is 1/4. I want that to happen twice. And I want her to fail, not get on a red bus, once. Into our calculator we go, and hopefully you guys get 0.1406. Okay, part 2 of that question, on at least 2 days. So, at least 2. What does that mean? It means greater than or equal to 2. Or in other words, I want the probability of 2 plus the probability of 3. Now this time it's multiple cases. I'm not going to do the 1 minus idea because it's only 2 cases. Okay, the 1 minus idea, I would have to get rid of 0 and 1, which is 2 cases. It doesn't save me any time. And to be honest, I already know this number because it's this one. So all I really need to do is figure out the 3 case. So 3, choose 3. She gets on a bus all 3 days. The likelihood of a red bus is 1/4. We want that to happen 3 times. Not red bus is 3/4. We want that to happen no times. So we're going to take our 2 separate answers and add them together. And if you do it, I'm hoping you get the same numbers I did, 0.15625. Okay, that's a binomial distribution. How to find the whole table, which we won't do very often. It's time consuming. It's not hard, it's time consuming. We prefer to look at specific cases, like we did here. Sometimes there's a single case, sometimes there's more than one case. Sometimes we want to use the indirect method, work backwards, get rid of what we don't want. You should also be able to figure out expected values. Okay. The homework you should try is right here. Give it a try. If you're stuck, come ask me and we'll look at it.